Okay, so welcome back everyone to the hardware panel. So this is the next session of quantum computing theory and practice, the session 2. And I can see the participant count is ticking up, so I'll just carry on talking until it sort of stabilizes. So in this session, we have a couple of activities. So first, there is a hardware panel discussion, which is chaired by Steve Brierley, who's going to introduce the panelists in a second. That goes on for about an hour. Then after that, there's another contributed talk by Yingkai Yang, and that will take us through until 12:30, which is lunchtime. And at that point is also a really good time to discuss any posters that you're interested in the posters channel after the session is finished. So I guess we're at about the right time to start, and we seem to have well over 100 participants, which is great. So without further ado, I'll hand over to Steve, who's going to introduce the next session. Steve.
Great, thanks Ashley. So we're joined here today by 4 of the leaders of quantum computing hardware development. It's a great privilege to have them here. So we've got Ilana Wisby from Oxford Quantum Circuits that develop superconducting quantum computers, Winfried Hensinger from the University of Sussex and from Universal Quantum that are developing trapped ion quantum computers. You can see Winnie's device in the background. And Fernando Gonzalez-Zalba from Hitachi, Cambridge, that are developing silicon-based quantum computers. And finally, Anthony Laing from Bristol and Duality Photonics that are developing waveguide systems with photons. So I think this gives us a great chance to understand each of the 4 platforms, to perhaps dig into a bit around the advantages of each approach and the challenges that they will face. I think this gives us a great chance to think about the vision for quantum computing hardware over the next 5 years and perhaps even longer. How do these systems scale up? What needs to happen in order to get to that point? And then finally, I think especially for this audience, there's a theory conference of software developers and people in the theory community to understand the technology more and find out what they can do to contribute, so we can work together to get to useful applications of quantum computers. So I'm going to start by just asking each of you to give a short introduction. It'd be great if you could introduce yourselves, a bit about your background and a bit about the platform and the approach that you're taking. Ilana, could I start with you, please?
Yeah, sure. Thank you very much. So as Steve introduced, my name is Dr. Ilana Wisby. I'm the CEO of a company called Oxford Quantum Circuits, OQC for short. Now, OQC, we build quantum computers. We are a hardware company. We span out from the University of Oxford back in June 2017, founded by Dr. Peter Leak out of the physics department over there. I have a PhD in quantum physics myself, but then I left for the world of startups. I've been doing startups more with AI, bot technology, software space for a number of years before joining OQC. Now, over 2 years ago, I had my 2-year anniversary just the other day. So at OQC, we have a unique approach to building superconducting quantum computers. We have a unique quantum bit. Now, a superconducting quantum computer is like one way of building this qubit technology. Basically, if you think about it, it's very similar to a regular circuit. You've got a silicon piece, you put some metal on top of it, difference being in the name, it's a superconducting metal. So that means you have to cool it down to kind of, first of all, around 10K or minus 260 degrees to get the superconductivity. You cool it down a little bit further to make it quantum. You add a special component, which is the magic quantum bit, the Josephson junction. And that's basically how you build a superconducting circuit. Great,
thanks Alana. Winnie, you've managed to shrink yourself down to the size of an individual atom. So could you tell us a bit more about yourself and the platform that's behind you?
Okay, Dave, thanks for organizing this. It's a lovely meeting, and probably the first time I give a talk at a conference out of my bedroom. So that's a new. And so I'm chief scientist and chairman of Universal Quantum. We are a full stack quantum computing company, and our mission is to build practical, useful, and large-scale quantum computers. Now, I'm also the professor at the University of Sussex and the director of the Sussex Center for Quantum Technologies. So we built a technology called trapped ions, and trapped ions have the advantage that they're room temperature technology. And we've been working on this technology for many years, but people felt it may be challenging to build a trapped ion quantum computer because of all the laser beams which one might require if you go to really large numbers. When I say large numbers or practical numbers, I mean maybe thousands or millions of qubits. And so at Sussex, we invented an alternative approach which incorporates applying voltages to a microchip in order to execute quantum gates rather than using pairs of laser beams. And what you see in the background right now is a second innovation which we develop as universal quantum. That is the idea to connect different quantum computing modules using electric field links. And that is different to alternative technology, which consists of photonic interconnects. And this way to connect different quantum computing modules can be very fast. And maybe more importantly, the engineering is very simple. So we've started 2 years ago as a company, and we are now really get going. We're just about to make a big announcement, and we're really in the middle of developing electronic quantum computing modules using trapped ions.
Great, thanks, Winnie. Fernando, could I pass over to you? Fernando's from Hitachi, Cambridge.
Thanks, Steve, for the invitation. And it's a pleasure to hear that so many people are joining the conference from all over the world. So yes, I'm Fernando Gonzalez-Zalba, Head of Quantum Computing for Hitachi Europe and Royal Society Industry Fellow. So for the last 5 years, I've been working on developing hardware for quantum computers, and more specifically one based on silicon technology. So silicon-based quantum computers use the spin 1/2 of an electron confined in a nano device as the qubit. And today I'm representing probably one of the newest quantum computing platforms in the world, since the first demonstration of such a qubit dates back to 2012. However, given that many of the fabrication processes that are used nowadays to make this type of qubits are compatible with those of the semiconductor industry, we see that there is a great potential in this technology to tackle the scaling challenge that all the quantum computing platforms are suffering at the moment. So that's the reason why major corporations like ours, Hitachi, are investing in this approach, because we see the potential for scalability of the technology. So in fact, recent breakthroughs from our group and our collaborators in nano device engineering have shown that silicon qubits can be manufactured in a very similar fashion to silicon field effect transistors, the MOSFETs that are in our computer processors, in our cars, in our mobile phones. And the fact that we can do this now opens an opportunity to leverage the know-how of the CMOS industry to build large qubit arrays. And this is what we aim to exploit in the next years. Thank you.
Yeah, thanks, Fernando. Anthony, could you tell us a bit about your work in Bristol?
Sure. So I'm Anthony Laing. I'm an associate professor at the University of Bristol, where I run a group in photonic quantum technologies and quantum simulations. I'm also the CEO of a recently founded company, Duality Quantum Photonics. Duality's aim is to realize special purpose quantum computers in the platform of integrated quantum photonics, where we'd like to target industrial applications and realize a quantum advantage in those applications on a 3 to 5 year timescale. So broadly, a quantum computer, whether it's special or general purpose, generates, processes, and measures photons. In a general purpose quantum computer, what you want to do is entangle those photons and measure them such that you can run a quantum algorithm like Shor's algorithm. Is going to take kind of millions or billions of components, and is a long-term journey, quite possibly. What we'd like to do in Duality is use the same kind of technology, integrated quantum photonics, and exploit kind of neat mappings between photons in waveguides and, for example, excitations in vibrational excitations in molecules to simulate molecular dynamics for industrial chemists. Back to you, Steve.
Great, thanks, Anthony. Okay, yeah, lots of really interesting points already. So I think what I'd like to do is just perhaps dig into to some of these points. Perhaps start by talking about the sort of advantages and challenges in each system, because I think the audience, is actually really well placed to try to to make use of those advantages and perhaps avoid the challenges. Fernando, you said something interesting, which was about the big promise of silicon qubits, that you're leveraging this CMOS technology. I mean, is that really true? Like, are the capabilities in a fab building mobile phone chips the same as can be directly used in silicon-based quantum computers?
Yeah, so to a larger extent, yes. So for example, the technology used in the 22 nanometer node, that is already quite old by now, are compatible with the designs or the geometries that we suggest for quantum computing applications. However, there are some challenges associated to quantum computing that are not present in classical computing, such as, for example, the routing of individual lines. So in a classical processor, you have billions of transistors and they are controlled with thousands of lines only. However, we have this challenge in quantum computing that at the moment we still control each qubit with one input line, and that's unsustainable. Mm-hmm. So there is a particular aspect there that we need to work on. The routing of individual lines is one of the major important challenges that is not solved yet at the foundry level. And there is another
scalability problem of wanting to address, let's say, 1 million qubits. You have to do that with one direction or with one line or with a small number of lines. So is that saying that each qubit needs to be doing something similar to the other qubits?
Yes, if you want to have individual control, you need to be able to deliver those signals to individual qubit. And I mean, there is one aspect of classical electronics that we want to adapt to silicon quantum computing, which is this shared input arrangement, in which by using a smaller number of individual lines interfaced by classical electronics, we can deliver signals to many qubits. And that's, I mean, although this problem is not solved yet at the quantum computing level, the fact that we can combine quantum and classical electronics on the same chip, on the same monolithically, on the same piece of silicon, it will enable us to try to tackle this particular challenging aspect. Mm-hmm.
So maybe I could just ask Ilana at this point. I mean, is this addressability question, how are people approaching that in superconducting systems?
Yeah, sure. So Fernando's absolutely right. Right now, for each individual qubit, you typically have an individual control line. So scaling with that kind of 1-to-1 ratio is pretty unsustainable. So there are many different kind of ways you can mitigate against that in terms of control electronics, some of which Fernando's covered there, but generally multiplexing of signals right down to the base layer, starting to think about electronic quantum control, bringing that a lot further down. You've also got it, of course, going in the opposite direction as well that we need to be thinking about. But yeah, typically we all know that we do need to be working on ways in which we can get those signals to those qubits in a more efficient and effective manner. And there's a huge amount of research and development going into that and different ways we can do that to control all different types of qubits and quantum devices, particularly when you're then operating at cryogenic levels.
So this cryogenic question comes up a few times. So you're controlling the qubits with a microwave system or microwave pulses. So that's adding energy into the system. Does that become a problem when you get to hundreds or thousands of qubits in a superconducting system?
Yeah, sure. It's a good question. It's one that's quite often cited as you'll boil your fridge over, which is for a start completely incorrect in terms of physical boiling. We're not dunking systems into cryogenic liquids anymore. But for a start, yeah, effectively what you have is you have your control wires. You send an electronic pulse down to the bottom of the fridge. As you're sending that pulse down, you're also thermalizing it, and you're getting to less and less and less photons as you get further and further down. So that energy is kind of going, is decreasing as you get to the bottom, so that you're doing quantum effects with single numbers of photons when you get down to the bottom typically. Of course, if you start to do that many, many times and you have many thousands or millions of photons, you still have quite a lot of energy down there. So we need to think about more about heat dissipation. So how do we mitigate against heat dissipation for controlling and scaling superconducting qubits? So we've already touched on a few ways you can do that. We can think about the multiplexing. We can think about locally generated control signals down at the cryogenic levels, like lower down. We can think about reflective filtering, new different types of amplification and filtering that's more effective and efficient, all trying to reduce that heat load so that we can maintain the cooling power. Now, with these near-term approaches, we generally think that we can get 10 to 100 times less heat load, which obviously makes scaling in that way a lot easier. But we also do know that these fridges, this tool can get bigger. For R&D, we want small fridges so we can iterate quickly with cooling times up and down. But if you're starting to think about a scalable, stable device, which you might want to only cool down, once a month and then leave, having a bigger fridge is completely fine. There are also a number of groups looking at how you might research networking fridges together. So that is also a different approach, thinking about having a number of linked systems. ETH Zurich, for example, they've announced recently they've connected 2 fridges together with a waveguide. So there's multiple different ways we can think about scaling before we're getting anywhere near boiling fridges.
So these fridges are actually connected at the cryogenic level, so that there's a quantum state passing between 2 fridges. Yeah, that's amazing. Okay, right. Thank you, Ilana. So Winnie, could you tell us a bit more about how your trapped ions are controlled? You mentioned that you don't use lasers. So how do you control the ions in your system?
So one of the key considerations for me has always been to think when we go to a larger number of qubits, to practical number of qubits. And obviously there's a different vision what maybe practical numbers of qubits are. Now, if you imagine millions of qubits, and that may well be required to do some of the error-corrected operations, we need to come up with new ways to execute quantum gates. And so in laboratories around the world, people use laser beams, a pair of laser beams directed on the location of an ion in order to execute a quantum gate. And while this has been done tremendously successful with really, really amazing fidelities, it's possibly hard to imagine how you could build a machine which then would feature millions of such pairs of laser beams. And so we've been working over many, many years in my research group and now at Universal Quantum to come up with ways how you could actually, in a way, take the advantages of the technology of a conventional quantum computer. And what I mean by that is use silicon microfabrication and the idea of applying voltages to a microchip in order to execute quantum gates. Now, that's not very easy to accomplish, but it can be done making use of modern microwave technology. So what we make use of instead of laser beams is microwaves, in a way the same microwaves as you have in your mobile phone. And we use these microwaves to then drive transitions within the ion. Now, there's an added complication, and that is that microwaves tend to have not much photon momentum. And so there's a little trick you can apply, making use of very local magnetic field gradients. These are generated simply by current carrying wires, which are integrated into the microchip. Now, making use of such current carrying wires inside the silicon microchip, you can now on a local level entangle 2 ions, and you can actually do this amazingly well, in fact, surprisingly amazingly well. And part of the reason is that microwave technology is just a lot more developed and a lot more, has much less errors in terms of like motion of laser beams, phase fluctuation of your laser beam, amplitude fluctuations, all of that is taken out and being replaced with an electronic source. And now the next step, it was required then to actually consider how we could implement such a design on a large scale. When I mean a large scale, I mean error-corrected quantum computer. Obviously, I'm very hopeful that NISQ applications will become important, and we'll find really interesting things to do at a small scale. But in order to build a quantum computer, I think it's important to have a system design that can really cater for these large numbers. And so having fully electronic quantum computing modules which can execute these quantum gates using by applying a voltage to the chip then allows us to really imagine building a practical quantum computer that could maybe solve some real world problems.
So Winnie, you a few years ago wrote a paper about building such a device that was getting bigger and bigger and bigger, and at some point it gets as big as a football field. And so now people are talks about this a lot of like, oh, Winnie's building this football stadium quantum computer. Is that still true? Or, I mean, do you regret saying the headline?
So in physics and in quantum information, there has been a long tradition that people write a lot of proposal papers, and some of these proposal papers are quite amazing. But many of these proposal papers share in common that they only incorporate the underlying physics principles, but not really the engineering considerations. Mm-hmm. Also, some of these papers share in common that they are quite ambitious or optimistic in what can be done on a certain time scale. So when we wrote in 2017 this blueprint to build a practical quantum computer, we set ourselves certain rules. And one of the rules was we can't just say, look, but in 2 years' time, we're going to have that, or things will be so good. We basically only allowed to bring in things we have either already accomplished or very simple interpolations, meaning like, you know, if I have twice as much current, then I can have twice as much magnetic field gradient or things like that. So with that in mind, we wanted to understand, is it actually possible to build a practical quantum computer that could host millions or even billions of qubits? Can we build a quantum computer that, for example, can break RSA encryption? And using these rules, we literally wrote an engineering solution of how that could be done. But because of the rules we imposed ourselves, we didn't say, look, you know, soon we're going to trap ions closer to the surface, soon we're going to have quantum gates faster, soon we do all these things. And so in a way, because of these rules and because of the tremendous ambition voiced in this paper, when we get to a particular part of a paper where we then discuss, okay, how would we go about having billions of qubits? We answer that question. Yes, it is possible, and yes, it would be the size of a football pitch if we now all retire and don't have any more physics innovations whatsoever. Now, obviously, that's not going to happen. But what we wanted to make the case, and I think that was something really exciting, that we are now moving away from being considered as some kind of fusion where we're always 10 years away from maybe building practical technology, where we have now the physics concepts worked out in such a way and to such a degree that we can now really say such a machine can be built. Is it easy? Not at all. It's a tremendous engineering challenge, and in a way, in the background of what you can see right now is the very realization of this engineering challenge, this animation of how this blueprint of how building a practical quantum computer would look like. So obviously people only look very often don't spend much time with papers, and so many times I've been told, oh, Winnie, you're going to build a football pitch quantum computer while IBM has a small quantum computer. Now the difference between our football pitch size quantum computer is that it hosts 1 billion qubits, and other quantum computers out there host maybe 53 or 73 qubits, and that's the big difference. Now, I do not expect that eventually our quantum computer design will be the size of a football pitch, not at all, because we're going to do a lot of work in increasing relevant fidelities in order to allow us then to have a much smaller system design. Would I be unhappy if that thing is the size of a football pitch? To be honest, I wouldn't care less, because I think if I can have a machine which successfully operates billions of qubits and which can obviously compete with supercomputers that are also the size of a football pitch, then that is not to worry at all. We have plenty of other big worries to deal with. But realistically, I still don't think that the machine will be the size of a football pitch, because we will make breakthroughs, and as such, the machine will be much smaller.
Thanks, Winnie. Yeah, I think these architecture papers and strawman models for how the whole system pans out are super important, because they help us identify where's the bottleneck, where's the next bit of innovation that needs to come. Yeah, thank you. Anthony, can we hear a bit more about waveguides? I mean, you also use silicon in the fabrication process. So how does that help in a photonic system?
So silicon is one option, and we can sort of leverage the tools that Fernando mentioned. But there are other material systems for waveguides as well. Silicon nitride, for example, and the advantage of a material like silicon nitride is that the photons can be a range of wavelengths from kind of visible 800 nanometers all the way through to telecom wavelengths. So we have choices over the kind of detectors that we use. We also need to be cryogenically cooled if we're using superconducting detectors, which are required to detect telecom wavelength photons. But at visible wavelengths, we can perhaps use room temperature detectors, avalanche photodiodes. The way that we control photons in waveguides is a bit different to the other platforms. Our photons kind of propagate through channels, so these waveguides in photonic chips. And you can switch between one waveguide and another through a phase shifter, which is where you locally change the refractive index in part of the waveguide inside of a Mach-Zehnder interferometer, which is like a photonic switch. And so one of the challenges for us is really how do we implement those switches, and how many switches do we need? So kind of the propagation loss, you know, the main error that we've got to deal with in photonics is the photon loss. So as photons propagate down waveguides, they have an ever-increasing probability of getting scattered out and kind of becoming lost. So you lose your photon or you lose your photonic qubit. But that's propagation loss isn't such a big worry compared to the depth of the circuitry that each photon's got to go through. So you know, depending on how many photons you've got on the kind of connectivity that you want, a photon might have to pass through a number of Mach-Zehnder interferometers, a number of phase shifters, and with each one it passes through, it's got an ever-increasing probability of being lost. So a key challenge for us is understanding how we can reduce the depth of circuitry, but still have kind of good connectivity among photons. And then also, how do we implement those phase shifters? So again, in a material like silicon, the way that you implement a phase shifter is through locally heating one part of the chip. And that takes time, like microseconds, and it's just not fast enough. So there are a number of options to kind of get around that. Optical switching. We could use another layer of photonic material that has what you call a Chi2 nonlinearity, which means that you don't have to heat part of the chip. You can apply voltage and use the electro-optic effect and do kind of much faster switching. So those are kind of some of the ingredients that we've got to deal with in photonics. Great,
thanks, Anthony. You mentioned in your introduction something I thought was very interesting, which was around building a special purpose device before the bigger goal of a large-scale quantum computer. Yeah. Could you expand a bit more on that and explain either what you have in mind or where you see that going?
Yeah, so I guess what we wanted to do in Duality was think, where could we imagine taking the technology that we have now in the next 3 to 5 years? Technology is kind of changing all of the time, and our platform will incorporate those changes as they kind of become available. But just using what we have right now, what's the most we can do with it was our thinking. And following this line of thinking, what we wanted to do is, instead of turning our photons into qubits, instead of turning them into photonic qubits, we wanted to look out there in the world and understand if there was a natural mapping, an analog style mapping. And so it turns out that, probably as many people know, that when you look at a molecule, when you look at the vibrations of a molecule, at least in the harmonic approximation, the vibrations in molecules are described by the same mathematics as photons in waveguides. So like an excitation in a molecular vibrational mode is the same mathematically as a photon in a waveguide. So we have this nice mapping. Then the question is that just kind of is that a curio, or can you really kind of do something with it? And it's become, I think, increasingly apparent in recent years just how important vibrations are in driving reactions. So for example, the way that hydrogen fuel is made across the world is in a process called steam reformation, where you take water and methane and heat them up with a catalyst, like a nickel catalyst. And what you get out is hydrogen fuel and carbon monoxide and your catalyst back. It turns out, so it was shown in a science paper in 2014, that if you excite vibrational stretches in the water molecules at the start of the process, you make the process more efficient, you get more hydrogen fuel out. But modeling this kind of process, these, maybe not that specific one, but these kinds of processes where you're modeling many vibrations in large molecules or different molecules that are kind of interacting, is computationally intractable. So the question for us is, can we take these kind of molecular dynamic problems and, using this smart mapping where photons and waveguides map to vibrations in molecules, can we model those kind of processes and discover something new? Could we increase hydrogen fuel production by 1%, for example? That would be a valuable advance.
And how is the theory that goes alongside that? I mean, do you know that if you build this device, it will have this kind of impact, or is this something that's still an open question that you'd like the theorists, for example, at the conference, to be addressing?
Well, we'd love the theorists at the conference to think about these kind of problems. For the small scale versions of the problems, we've published papers a couple of years ago in Nature, for example, where we showed that we can use a photonic chip as part of a feedback algorithm to design a kind of a control field that would disassociate ammonia through a preferred pathway and suppress dissociation of ammonia through kind of undesired pathways. So that's kind of a key building block in this picture. And yeah, what remains to be done is to kind of scale up these ideas to larger molecules, to molecules associating as well as disassociating.
Thanks, Anthony. Maybe Ilana, could I ask you a bit more about these kind of near-term applications? Is there one or a few that you're particularly excited by?
I think that the example that Anthony just gave was really beautifully put, actually, and really highlighting the quantum simulation side of things as particularly interesting, both commercially, but also for these NISC near-term applications. For us, actually starting to identify more of what they are, what's commercially interesting, and then for the theorists, understanding what kind of benchmarks, what algorithm points, proof points, toy demonstrators we can start to put in place to showcase progress towards that stage is super important. So that's something we'd be really interested in working with theorists on, identifying those, but also working with kind of the end users, the commercial entities, so that you can kind of bridge either side. What's capability now, where's capability in the future, and what's interesting for commercial applications to end users.
Thanks, Alana. Fernando, maybe I could bring you in on this discussion. So where does Hitachi see the route to taking this great technology and turning it into a commercial application, if that's something you're able to talk about? It'd be super interesting.
Yeah, definitely. So in short, Hitachi is quite interested in quantum algorithms with applications in the finance sector. historically, this comes from the fact that, I mean, Hitachi is quite a large company and has a section of new computational paradigms. And also we do research on another type of ASIC, an Ising-based computer. Basically performs classical annealing and is particularly useful for optimization problems. So, this type of ASIC has found applications in the finance sector. Now, Hitachi would like to replicate this particular approach on quantum computing, and we've already started looking at some particular cases of quantum algorithms for finance, and we see the potential of silicon-based quantum computers to implement those algorithms. Particularly, what we are seeing is that given the speed of some of the quantum gates that can be implemented in silicon, particularly the ones driven by exchange interaction between the spins, so basically qubit gates, we may be able to perform some of these algorithms faster in the near term than any other architecture or any other.
That's interesting. So, I mean, from your experience with ASICs, I mean, that's a different kind of technology, but what is it that is needed to get from the hardware technology to the applications?
So there needs to be an interface. There needs to be another type of scientist or researcher or engineer in between the people developing the algorithm and the people developing the hardware. Needs to be people with understanding of the mapping between the two, because you are going to find customers that learn the quantum computers are going to be very useful to solve some particular algorithms, but those algorithms do not map straightforwardly into your hardware, into your architecture. So that process is not trivial, and it needs to be worked out. For that purpose, we have people in Hitachi and we have collaborators looking at that particular aspect of the process. Yeah, so I think that's I don't know if you'll be talking about this aspect in the conference, but I think it's something that I don't hear so much about it, but it needs to be.
Yeah, Ilana, I saw you were nodding away. Did you want to add anything?
No, I completely agree. There's this gap between obviously the algorithms and the hardware, which is a really important gap to fill when it comes to control software and interpretation. How do you turn something that's a theoretical algorithm, something that's practically optimized, depending on what hardware you've got? And I know that there's a lot of people, including ourselves, of course, and this is a hot topic for the community that we're all working on together.
Winnie, perhaps changing topic a bit. So, sort of where do you see quantum computing going in the next 10 years? What's your sort of vision for your platform?
So my vision might be a little bit different to different players in the field, in the sense that I think a very, very strong focus has to be in engineering. So it's really needs to be all about the engineering and realizing these integration challenges which we are facing now. So we really need to push all the several engineering challenges, and they need to go out of the academic research lab, and they need to be done by professional engineers. And to be honest, that's really the reason why we started Universal Quantum in the first place, because we realized that within the research group it was difficult or impossible to really build devices with the required yield and the required quality in order to achieve that. Now, I'm very interested in learning about NISQ applications and short-term applications, and I think there's a lot of tremendous momentum in this field, but I'm not yet quite convinced that we will see the key applications within that. And so for me personally, I see NISQ more as a proving ground for the engineering technologies we develop, rather than a goal in itself. And what my vision for the 10 years timescale really is about really demonstrating the key engineering challenges in going to large scale. Like we are not, universal quantum is not in the game of maybe, getting to 83 qubits and like arm wrestling whether we have now quantum supremacy or not. I think it's very interesting, and I'm very thankful and happy that some people are doing that, because we learn a lot out of this. But personally, I feel it's most important to address the big engineering challenges. And so what we do as a company, but also what I feel is really important for the field, is in bringing all of these together and to really demonstrate that we can go to a large scale. And so making predictions in time is always very challenging, and people tend to get it awfully wrong. And so I'm not going to try to say what exactly we will have in 10 years' time. But certainly as a speaking for the work we do, and I think I'm much more comfortable speaking about myself than speaking about others. So as a company, we will make distinct engineering, we will take off distinct engineering challenges to build machines that are inherently scalable. And the word scalable, again, is like used in so many different contexts, and there's so many different interpretations. It's very hard to bring my own interpretation in without being ambiguous. So what I really mean is that we can build small-scale quantum computing modules where maybe the number is not so important, but that these are truly can be manufactured in such a way that you can just add more and more of these machines. We will use small-scale algorithms in order to test these machines, because at the end of the day, there are things out there to give us a feeling of the power of a machine. For example, the quantum volume invented by IBM is one of them. But at the end of the day, it's critically important to benchmark the machines with interesting applications. And this is, I think, where I'm feeling really enthusiastic about this conference and about the work being presented here, because this is really a fantastic grounds for us to learn of what we can do as first applications with the machines we develop. And I'm not holding our breath necessarily that we're gonna do the groundbreaking and the most powerful applications in the next 5 years. I think it's really about demonstrating the technology, but hopefully do this in such a way that we can actually already do something useful. And that's really, for me, maybe the other thing which is absolutely critical in the work we want to do, is we want to engage in useful applications as early as possible, and maybe focus more on a useful application that may not deliver immediately, rather than trying to do things which may not be so useful, but maybe potentially more powerful than a conventional computer. Everything is slower than we planned for, so there's no question there's many challenges to overcome. But I think the good news is that we are now really, I would say, on a roll in the sense that things are really moving now. So it's an unbelievably exciting time, and I'd like to pass this on maybe to all the viewers of this panel. This is what you do and what you work on in the next few years is critically important, and for really for the first time we'll be able to do some of these things in the lab, and so I think this is going to be some of the best 10 years possible for anybody who's working in the field.
Yes, agreed. Yeah, thanks, Winnie. I liked your phrase, arm wrestling, and I thought I wanted to just ask a question to Alana before we go over to the questions from the audience. I think last year there was a lot of arm wrestling, especially from the US, in terms of qubit numbers in superconducting systems. That seems to have calmed down a lot now, and there seems to be a bit of a pause on that. Why do you think that is?
Yeah, I mean, we definitely saw a lot of announcements last year. I think there were some key milestones that were set that it was great to see people delivering on, because there was a bit of danger if people weren't going to deliver on it soon, that things might fall to the wayside. So yeah, I'm very pleased that they were able to deliver on those. But up until recently, with milestones that were set like that, that has been focused on scaling of devices, on qubit numbers. Actually, if you start to go to a number of the key conferences over the past few years, the conversation, of course, has not been about scaling and qubit numbers. It's really been focused on the quality of the qubits that you can create. And a lot of these other competitors have been talking about the work they're doing on smaller devices to improve a lot of the underlying metrics at a small scale, which of course is music to our ears, because we don't want to be chasing numbers. You can add more and more and more qubits without adding capability in a very, very stupid way. And there's just no value in doing that. I mean, we've already seen Google move from their 72 qubit device down to their 53 qubit device to prove out supremacy. A lot of that was around making sure they had the gate fidelities and the lower crosstalk required over the qubit number. The same with IBM. They've got bigger devices, but actually for their quantum volume, they're focusing on 20, 30 qubit devices. So I think as a general trend, it's in my opinion, it is the right thing to be doing, to be taking that step back, not to be chasing the scale and the number hype. But of course, once you get to a point where you're no longer limited by the quality and by the control, at that point, it's more appropriate to start thinking about scaling. Great.
Thank you. So we got questions from the audience, and Leonie has very kindly offered to help with this, and has been watching the Slack channel. Could I pass over to you, Leonie? Do you have questions already?
Yeah, there are lots of questions here, lots of good ones, and this one fits very well with what Alana just talked about. It comes from Joel Klassen. How closely do you expect large-scale quantum computers to look like the existing small-scale examples? Are these entirely different engineering problems, or are major theoretical insights still required? I think there was a word missing in I hope I got that right.
Fernando, would you like to start us off on that? That's a great question.
Yeah. I mean, here you can follow two approaches. Probably my favorite one is to follow up a bottom-up approach in which you work really, really hard on getting your single qubit gates, your 2 qubit gates right. You come up with an optimal tile design that allows you to scale in the second dimension, and then you go up from there. So if you follow this approach bottom-up, then you would imagine that the chip that contains the hardware will very much look like an arrangement, a matrix arrangement of those structures that we are looking at now. There is another interesting approach that is worth looking at, which is a top-down approach, which may end up leading into chips that look different from what we see now, in which basically you try to go for goal, design very large structures that may contain a large number of qubits, and demonstrate that those qubits can work in a high-density environment, which is not trivial. And this is an aspect that is part of the engineering challenge. No, it's we see in literature lots of work from researchers at the 1 qubit, 2 qubit gate level, or as a small number of qubits. But when you go, or when you aim to go into the NISQ era or beyond the NISQ era, you need to already start showing some work following this approach, the top-down approach that demonstrates that you can get all those very good numbers that you're getting in a high-density environment. So this is an aspect that I think it's being neglected at the moment by corporations, but it's something that it needs to be looked at as well. What happens when we try to manufacture the real thing? What are the challenges that occur in that high-density environment but that we don't see right now?
Thanks, Fernando. Should we take another question, Leonie?
Yes, this is also a general one. David Shaw is asking, what do the panel members think of IBM's quantum volume as a general cross-platform figure of merit for the NISQ era?
Any takers?
Yep. So
this could just be a thumbs up or a thumbs down.
okay. So as I'm happy to give my opinion. I think it's very interesting. I think we've actually just written a paper, so I can advertise that. It's on our website where we compare different architectures and make use of the quantum volume. It's probably the hardest measure, and potentially it's much easier to or the architectures can perform better than the quantum volume may promise. But it's certainly a good comparison, and we are using it to understand our architecture. But at the end of the day, the real comparison will derive from running practical applications, and some of these applications may not require the full bandwidth of what the quantum volume really tells us. The quantum volume is maybe very general measure, and as such probably like the right measure as such, but it's not necessarily always the best measure in terms of a given application. And so I think it's helpful, but I wouldn't overinterpret its meaning.
So do you have an alternative? Would it be essentially just pick an application and see how well it does?
Yeah, to some degree. I mean, also maybe think of the gate sets, that maybe the native gate set to use rather than go on the most general gate set, and also think of applications. And particular applications may not require a lot what is encompassed in the quantum volume.
Great. Should we have another question, Leonie?
Yes, sure. So this is one for Ilana from Jacinta May. On an experimental level, how do you deal with the noise associated with working on superconducting qubits at cryogenic temperatures? And how does error correction fare when superconducting computers are scaled up?
Yeah, so sure. So there's two parts to that. The first being the noise element itself. So as we know, there's lots of different types of noise and noise mechanisms that we need to make sure that we can mitigate against. This is really where OQC's kind of core technology and USP comes in. So we've redesigned the qubit, the quantum device itself, with a lot of these noise mechanisms in mind. One, of course, being crosstalk. So we have some of the lowest crosstalk that's ever been reported, actually, publication to come. But we're really, really excited about that. So that's one example of it. With regards to other different types of noise processes, I can geek out on this for hours because this was actually a large part of my PhD. So look up some of the Nature Comms papers on slow noise processes out of NPL. Kudos to John Burnett for that. But yeah, this is still like partly an engineering, almost material science problem when you start to think about some of these two-level systems and understanding them. And there's a lot of R&D that's still to be done there. But for us, you know, it's really thinking about the device design, simulation, making sure that we're designing it with thinking about all of these different losses mechanisms in mind, and what's really, really important, and how we structure devices for the best performance for now, as well as then, of course, mitigating against that in the future. The second part was in terms of thinking about error correction and what we think that was in the future. Can I just confirm that?
Yes, how error correction will work.
Yeah, maybe I could jump in and say, perhaps just to refine the question a little bit. So, you know, quantum error correcting codes typically assume a general level of noise. So they would typically assume a depolarizing noise, for example. And so to what extent does that noise model map well to superconducting systems, and are there particular types of noise that we should be thinking about in error correcting codes, in designing new codes?
Yeah, so this is one of the reasons that we actually really love working with quantum theorists and also people that are working on the algorithms, because this is a key question. It's something we can co-design together, because you can map these things a lot better onto the hardware if you have a fuller understanding. So there's a lot of knowledge transfer that can still optimize these things. We should really, for now, be viewing this kind of error correction as a near-term tool for improved computation at this point. and what schemes we can use now to create better algorithms based on the error corrections available to us at this small scale. What that looks like in the future, and understanding what the noise processes will look like as a system scale is a bigger question that we would need to take offline.
Yes, and I should say we absolutely should continue the discussions on the Slack channel after this panel, perhaps in the break time after the next talk. Do we have another question, Leonie?
Sure, there's one to Anthony from Alexander Krienko. I'm sure I did not pronounce that name correctly. Please apologize. So the question is, what is the main bottleneck for performing digital quantum simulations with the optical platform? And if increased optical linearity is required?
Yeah, I guess Alex has hit on both one of the bottlenecks and a potential solution. So the two main kind of bottlenecks we've got to deal with in photonic quantum computing are photon loss, as I mentioned before, and also entangling photons. So, photons famously are non-interacting bosons, and therefore the kind of mechanisms to entangle photons, at least in linear optics, are not straightforward. The best method that we have right now is kind of probabilistic gates that are heralded with ancillary photons. Those have been shown to work well, but because they're probabilistic, we end up needing to kind of multiplex many of them. And there's a kind of blow up in componentry in photonic circuits. So as Alex pointed out, if we had some kind of like intrinsic nonlinearity mediated through some light matter interaction, that would kind of alleviate one of these bottlenecks quite sort of dramatically. But right now, those kinds of solutions don't work as well as the post-selected gates, even when you factor in the kind of the blow up in physical resources.
Great. I think we're quickly running out of time, so I'm just going to perhaps summarize the discussions, and we'll leave the rest of the questions to the Slack channel. So please do go answer those questions. I'm sure there were lots of really interesting ones. And I think there are quite a few things we haven't discussed. We didn't talk about the speed of the systems, of the gates. We didn't really talk about cost. Actually, I was wanting to ask you all how much it would cost me to build a quantum computer myself if I had anywhere near the ability, which I absolutely do not. We only touched briefly on error correction. I think that's a really interesting topic. Matching error correcting codes with the error rates is I think fascinating. I mean, I think what's come across is the remarkable level of physics that's involved in all of these platforms. I mean, controlling individual spins in electrons or atoms and photons, is really exquisite at this point. I think so. I was at a conference 5 years ago, and the general feeling in the theory community was that it was going to be almost impossible to build a quantum computer. And I think, as Winnie said earlier, this is just such an exciting time to be in this field because of the progress that's been made over the last 5, 10, 15 years. So yeah, really happy about that. The level of innovation is obviously huge, and I can see you all have different visions. I think that's really interesting because it's obviously related to the different advantages of your systems, and so I'm fascinated to see how this plays out over the next year. There's clearly some big engineering challenges, both in the hardware, and then we started to talk a bit about the integration with the software and the theory level. So I think we should have this panel again in a year's time, and I'll be fascinated to see the progress. So thank you all.